So hi everyone, this is lecture 7 for the NPTEL course Introduction to Algebraic Geometry and Commutative Algebra. So this is week 7 of our TA session. This TA session is named as Module of Fractions and localization. So for the preliminaries, in the following exercises, let A be a commutative ring, and for S is a multiplicatively closed subset in A, and an A module V, and let IVS let IVS be a map from V to S inverse V, and which maps from x to x by 1 and be the natural map, and with the natural scalar multiplication S inverse A cross S inverse V, go to S inverse V as A by S comma x by t goes to AX by ST and the abelian group S inverse B is endowed with the S inverse A module structure. Now we come to our first problem that says that let A be a commutative ring and be a finite A module. Okay, and show that and small a of capital A and ideal such that V equals to AV, show that there exists small a from bold A such that 1 plus A of V equals to 0. Now we prove first via localization and Nakayama lemma. Since V equals to bold AV, we have for every maximal ideal M of A, V suffix M equals to AV suffix M equals to A suffix M into V suffix M. If A is not contained in M, then A suffix M equals to capital A suffix M. Hence, V suffix M equals to A suffix M, V suffix M equals to V suffix M. Gives no restriction. Now, if bold A is contained in M, then A suffix M is contained in M A suffix M. Thus, V suffix M equals to A suffix M V suffix M, which is contained in M A suffix M V suffix M equals to M of V suffix M. Since Vm is finite AM module, Nakayama lemma says that V suffix M equals to 0. Hence, for every ideal M containing A, Vm equals to 0. By exercise given in your assignment, if a finite module localizes to 0 at all maximal ideals containing A, then there exists B of A1 plus A such that BV equals to 0. Thus B equals to 1 plus A for some A of bold A and 1 plus A of V equals to 0 as required. So this is one way of proving this. Now, more elementary proof which uses inductive argument that says that suppose V is generated by x1 up to xn and set Vi equals to ax1 plus up to axi. We prove by induction on j equals to 0 to n that there exists small aj of bold A such that 1 minus aj of V is contained in A of V of n minus j. And for j equals to 0, since V equals to AV, we have xn equals to summation bk xk with bk belongs to A. Thus, 1 minus bn of xn equals to summation of k equals to 1 to n minus 1 bk xk contained in AV n minus 1. Hence, taking A0 equals to bn gives 1 minus A0 of V contained in A of Vn minus 1. Assume inductively that there exists aj of A such that 1 minus aj of V is contained in A Vn minus j. Restricting to Vn minus j and repeating the argument for the generator xn minus j, we obtain aj plus 1 is contained in A such that 1 minus aj plus 1 of V is contained in A of Vn minus j minus 1. Proceeding inductively for j equals to n, we obtain that an is contained in A such that 1 minus an of V is contained in A of V0, but V0 equals to 0, hence 1 minus an of V equals to 0. Setting A equals to n gives us the desired result. Now, we focus on our next problem. Let A be a non-zero commutative ring and S0 the multiplicatively closed subset of non-zero divisors in A, and Q of A equals to S0 inverse of A, the total quotient ring of A. And A module V is called a module with rank over A if S0 inverse V is a pre-QA module. In this case, we define rank of V over A equals to rank of S0 inverse V over QA. Now we have to prove that every pre-A module is a module with rank and its rank is the cardinality of an A basis. If A is an integral domain, then every A module V has rank, and rank of V over A equals to rank of dimension of S0 inverse V over QA. And if V is a module with rank, and then S0 inverse V admits a QA basis of the form xi by 1, where xi is a maximal A linearly independent family in V, and for D, every finite torsion-free A module with rank is isomorphic to an is a module of a finite free A module. Now we have to prove these first statements. So I suggest first you read and understand this, then we will start solving. Okay, so let us start solving the problems. Uh, okay. Uh, 1 second. What is happening? Okay. So yeah, so let us start solving the first problem. Let V be a free module with basis EI. Localization commutes with direction, hence S0 inverse V is isomorphic to S0 inverse of A, where I is of A. Now, but S0 inverse of A equals to Q of A, so S0 inverse of A is isomorphic to S0 direct sum of QA, where I is running from capital I, and which is a pre-QA module with basis EI by I. Therefore, V has rank, and rank of A, rank of V over A is mod of I, the cardinality of an A basis of V. Now, for the second question, it says that if A is an integral domain, then every A module V has rank, and this rank equals to S0 inverse, dimension of S0 inverse V over QA. Okay, so assume that A is an integral domain, then S0 equals to A minus 0, and QA is the field of fractions of A. For any A module V, the localization S0 inverse V equals to QA tensor V over A is a vector space over the field QA. Every vector space admits a basis, hence is free. Thus, every A module has rank. Moreover, by definition, rank of V over A equals to rank of S0 inverse V over QA, which equals to dimension of S0 inverse V over QA. Now, for the C, the question was, if V is a module with rank, then S0 inverse V admits a QA basis of the form xi by 1, where xi running from small I from capital I is a maximal A linearly independent family in V. Now, let V be a module with rank, and let small xi from where small I is running from capital I be a maximal A linearly independent family in V. First, we show that small xi by 1, where small I is running in capital I, is QA linearly independent. Suppose summation of AI by Si into Xi equals to 0, with small ai belongs to capital A and small si belongs to capital S0. Clearing denominators, there exists small s from capital S0 such that summation of bi xi equals to 0, where small bi is running from capital A. Since the small xi are A linearly independent, then all bi equals to 0, hence all of ai by si equals to 0. Thus the family is QA linearly independent. Now, maximality implies that for every small x of capital V, there exists small s from capital S0 such that Sx belongs to summation of Axi, where your I is running from capital I. Dividing by small s in S0 inverse V shows that small x by 1 lies in the QA span of xi by 1. Thus, xi by 1 generates S0 inverse V over QA. Since S0 inverse V is free, this family is a basis. Now, for the D, every finite torsion free A module with rank is isomorphic to an A submodule of a finite free A module. So D says that let V be a finite torsion free with rank smaller. By C, choose small x1 up to small xn in V such that xi by 1 form a QA basis of S0 inverse V. Define a homomorphism phi from A to the power R to V where EI is going to xi. Now localizing at capital S0, we obtain that S0 inverse phi is QAR to S0 inverse V, which is an isomorphism because sides have the same basis. Hence car phi localizes to 0 and you can see that S0 inverse of car phi equals to 0. Thus car phi is a torsion submodule of A to the power R, but A to the power R is torsion free since S0 consists of non-zero divisors, so car of phi equals to 0. Therefore phi is injective and V is isomorphic to image of phi, which is contained in A to the power R. Thus V is isomorphic to an A submodule of the finite free module A to the power R. Now we move to our next question, which says that let A be a commutative ring and V a projective A module. That is, V is a direct summand of a free A module. Let S0 be the multiplicatively closed subset of a non-zero divisors in A. If S0 inverse V is finite QA, which is S0 inverse A module, then V is a finite A module. In particular, if A is integral domain, then a projective A module is finite if and only if it has finite rank. So you have to prove this first. Let us understand the problem, then we will do this. Okay, so let us focus on question 7.7. So let us start doing the solution. So step 1 says that embed V into a free module. Since V is projective, there exists an index set I and a free A module F equals to a to the power I such that F is isomorphic to V direction W for some A module W. In particular, we have an embedding F from V to F A to the power I. Now, in step 2, if we localize this, localization preserves direct sum, hence S0 inverse F is isomorphic to S0 inverse V direct sum S0 inverse W. But S0 inverse F is isomorphic to Q of A to the power I, and by assumption S0 inverse V is a finite QA module. Since it is a direct summand of the free QA module QA to the power I, it is itself a free QA module of finite rank R, and S0 inverse V therefore isomorphic to QA to the power R. Now step 3 says that finiteness forces I to be finite. Consider the localized embedding S0 inverse F from S0 inverse V to Q to the power QA to the power I. Since S0 inverse V is isomorphic to QA to the power R is generated by R elements over QA, its image lies in the QA submodule generated by finitely many basis vectors of QA to the power I. Therefore, only finitely many coordinates of QA to the power I are involved in the image. Hence, there exists a finite subset J in I such that S0 inverse V is a subset of QAJ. Since localization is exact and F is injective, we obtain that V is contained A to the power J and A is A to the power I. Thus, V is contained in a finite free A module. Now, step 4, conclude that V is finite. Since AJ is a finite free A module and V is a direct summand of it, because V was a direct summand of A to the power I, it follows that V is a finite A module. Now, the final statement for the integral domains, which says that if A is an integral domain, then QA is its field of fractions, and a projective A module has finite rank if and only if S0 inverse V is finite dimensional over QA. By the result proved above, this is equivalent to V being finite. Now, let us focus on to our next and last problem, which says that let K be a field and I an infinite index set and A equals to K to the power I and small a equals to K to the power I, which is contained in capital A, the ideal of families with finite support. Now define S as small si from I belongs to capital I, which belongs to K to the power I, such that Si is not equals to 0 for almost all I, then S is multiplicatively closed in A, and so that the canonical homomorphism phi of A by small a is S inverse hom of A by A of comma A to S in hom of S inverse A by A comma S inverse A over S inverse A is not surjective. The B says that for every infinite set J, so that the canonical homomorphism phi of Aj from S inverse hom of Aj comma A over A to S hom of S inverse Aj minus comma S inverse A is not injective. Now you understand this problem for 5 minutes, then we will start. cabbage the Okay, so let us start solving this. So for the first question, let us start from the preliminary observations. The first observation is that since K is a field, we have K A equals to K to the power I is a product of fields, and small a equals to K to the power I consists of elements with finite support. And observation 3 is that if small s belongs to capital S, then Si not equals to 0 for all but finitely many I. Thus S is invertible in A modulo small a, and in fact S inverse of small a equals to 0. I mean, if small x belongs to A, then x has finite support. Choose small s from capital S, vanishing exactly on that finite support. Then small s x equals to 0 in capital A, hence x by 1 equals to 0 in S inverse A. And consequently, you can see that S inverse of A mod A is isomorphic to S inverse A. Now, the first question, to address this question, we will show that phi of A mod A is not surjective. First, compute that Hom of A mod A to A over capital A for any A module M, Hom of A mod A to M over A is isomorphic to annihilator of A over M. I mean, if you map small f to f of 1, you can see that this gives this identification. Thus, Hom of A mod A comma A over A is isomorphic to annihilator of A mod A over A. But if A belongs to capital A satisfies A of A equals to 0, then for every small I of capital I, we can choose EI of A with support small I. Then EIA of I equals to AI. Hence AI equals to 0 for all I, so A equals to 0. Therefore, annihilator of A of small a equals to 0. Hom of A mod A, comma A over A equals to 0, and hence S inverse of hom of A mod A, comma A equals to 0. On the other hand, S inverse of A mod A is isomorphic to S inverse of A. Therefore, hom of S inverse A of S inverse A mod A, comma S inverse A is isomorphic to hom of S inverse A, comma S inverse A over S inverse A is isomorphic to S inverse A. And since this is non-zero, the target is non-zero, thus the canonical map from 0 to S inverse A is not surjective. Now for the question B, if you look at it, phi of A to the power j, we have to show this is not injective. Now let us take j to be infinite and first compute that hom of A to the power j comma A over A is isomorphic to A to the power j. Since a homomorphism is determined by the image of its basis vectors, thus hom of A to the power j comma A of S inverse is isomorphic to S inverse of A to the power j. Now on the other hand, S inverse of A to the power j is isomorphic to S inverse A of j. So hom of S inverse to the power j comma S inverse A over S inverse A is isomorphic to S inverse of whole of j. The canonical map is induced by localization. This map S inverse of AJ goes to S inverse A of j, and we now show this map is not injective. Choose A to the power j where small j is running from capital J, such that AJ has finite support and the supports are pairwise disjoint, which is possible because I and j are both infinite, and then each of A to the power j coming from bold A. Hence for small j there exists Sj of capital S with Sj of A to the power j is 0, and taking the common multiple smallest from capital S, killing finitely many coordinates at a time, we obtain that S of A to the power j where small j is running from capital J is 0 in S inverse A of to the power j. Thus the element is non-zero in S inverse of A to the power j, but maps to 0 in S inverse A of j. Hence the canonical map is not injective. Therefore we have proved the following, and we have done all the questions from today's assignment. So we will meet in the next class.